Welcome to Sage Audio. Today we're talking about how to fix masking. But first, if you have a mix that you need mastered, send it to us to receive a free mastered sample of it with the link in the description. How frequency masking works. Before we start talking about how to fix masking issues, let's get a better understanding of what it is. When we discuss masking in producing, mixing, or mastering, we're usually discussing spectral masking, in which lower frequencies tend to mask or cover up higher ones. For example, if I played a 500 Hz sine wave while simultaneously playing a mix, that wave would, to some extent, cover the mix. In other words, we'd perceive less of the original mix than if the mix was playing by itself. So let's listen to these two signals, first only the mix, then with the sine wave added, to see if we perceive less of the mix. The most important, frequency range. In the last chapter, I briefly showed a graph that shows how 250 Hz covers up other frequencies, but let's look at it in greater detail. So the red bar represents a sine wave, which if we observe the x-axis, we'll notice it's at 250 Hz, while the y-axis shows the amplitude of the sine wave. Combining the y-axis with the white curved lines will show how much masking occurs to various frequencies. It's a little convoluted, but I'll explain it in better detail with some examples. So let's say that the sine wave is 40 dB, so at around 500 Hz, the sine wave would mask about 30 dB of that signal. If, for example, the sine wave is 70 dB, then 2 kHz will be masked by it by about 30 dB as well. So similar graphs exist for a 500 Hz sine wave, a 2 kHz sine wave, and so on, but 250 Hz and slightly below is by far the most destructive or impactful when it comes to spectral masking. So let's listen to a mix again and play 250 Hz to see if it masks our mix more than the 500 Hz sine wave that we used in the previous demonstration. If you're enjoying the video, hit the like button. It helps us bring you more videos. Reduce amount of complex signal. In the past two chapters, we've been discussing only spectral masking, but this one covers both spectral and a psychoacoustic phenomenon often called the cocktail party effect. In short, our brains can only focus on so much stimuli at once, so the more instrumentation that we have, the less we perceive. And what's interesting is that if we reduce the amount of instrumentation, we reduce this effect and the spectral masking due to there being less competing frequencies. So let's listen to a mix and enable each stem one at a time to see if we begin to lose detail both from a spectral perspective and in terms of what we can perceive. Using EQ to fix masking. Now that we better understand masking, let's spend the rest of the video considering ways to lessen its effect. The simplest way to reduce masking is with an EQ. We can create a Bell filter over 250 Hz for that general area and reduce it by up to 3 dB on a full mix or more on individual instruments. Additionally, we could amplify higher frequencies. So let's listen to a mix with a cut in the lower range and a boost to the higher range and notice how we hear more detail come through. Only a small percentage of people that watch our videos are subscribed, so if you're enjoying the video, consider subscribing. It's free and you can always change your mind. How saturation affects masking. Saturation can both improve or worsen the effect of masking. For example, if the saturator introduces a second-ordered harmonic, this is going to amplify lows, which will likely increase masking to higher frequencies above that fundamental. But if we saturate higher frequencies, we could expect the opposite effect. Let's listen to saturation on low frequencies, then saturation on high frequencies, and notice how the first creates masking, while the second creates a clearer sound. Using compression to fix masking. How compression affects masking is a complex topic. By reducing dynamics and then amplifying the signal, we can reduce masking by bringing quieter parts of the signal upward. Additionally, we could reduce masking if we isolate the compression to the low frequencies, having a similar effect to the EQ that we used earlier. So let's listen to multiband compression with only the lows compressed and notice how the effect of masking is reduced. Using linear phase to avoid masking. If you're using any form of parallel processing, it helps to use linear phase settings to avoid temporal masking, also known as phase cancellation. For example, if I set up a parallel signal and I use an EQ to isolate the highs, timing differences between the two signals is going to cause temporal masking. By enabling linear phase on the EQ, I create a predetermined delay amount for the processor that my DAW can now compensate for, in turn eliminating temporal masking. So let's listen to this first without linear phase enabled and then with linear phase enabled. If you're enjoying the channel, join the community with the link in the description. Upward compression masking trick. The reason I wanted to discuss temporal masking in the last chapter is so I could share this tip with you. So let's set up a parallel track, and knowing what we know now, use a linear phase EQ. Like before, I'm going to isolate the high frequencies using the EQ. Then I'll insert an upward compressor, which is going to capture, compress, and amplify quieter parts of the signal. In this case, only the high frequencies, since we just isolated them. With this trick, we're using compression to reduce spectral masking, since the quieter parts of the highs are now going to be louder and more capable of competing for space with the more powerful low frequencies. So let's listen and notice how we can perceive a lot more detail. How oversampling affects masking. Oversampling increases the frequency range that a signal can occupy, in turn, reducing something called aliasing distortion. Aliasing distortion occurs when frequencies exceed the limits of our session sampling rate and bounce back down the frequency spectrum in the form of out-of-key, unpleasant-sounding distortion. Aside from having an unpleasant timbre, this distortion is going to cause both spectral and temporal masking to our higher frequencies. So let's listen to a mix with processing that would cause some aliasing, and then this same mix, but with our processors oversampling enabled. Using Gullfoss EQ to lessen masking. In Chapter 4, I said that EQ is the easiest way to reduce masking, but the Gullfoss EQ, which automatically adjusts the response of a signal to reduce masking, is even easier. All I need to do is increase the recover function and maybe some of the tame function. After measuring the incoming signal, the EQ creates a curve that alters the relationship between frequencies to best suit how our ears perceive complex signals. Let's listen and notice how the EQ works surprisingly well and consider how it accomplishes something that isn't possible with a typical EQ. If you have a mix that you need mastered, send it to us to receive a free mastered sample of it with the link in the description. Thank you so much for watching.